Good morning everyone. This is Shalini Tamar and today we are dealing with soil mechanics and foundation engineering. And this lecture is on index properties of soil mechanics. Index properties. Well, what are the index properties? First thing we should know, why we are finding the index properties. Well, the index properties are basically used in identification and classification of soils. That is the reason that we are dealing with these index properties. Well, what are all the terms that comes in the index properties? Well, one of the main index properties is water content of soil. Then next, specific gravity. We have dealt with these two terms, that what is water content, what is specific gravity. Today we are going to find that how we find these values in laboratory. Third, particle size distribution. Particle size distribution. Next important index property is consistency limits. Consistency limits. Next is in situ density. When I say in situ, it means that field density. Now, the first property, index property, is water content. There are various methods to find the water content of the soil. Water content. Well, water content of a soil is very important parameter that control its behavior. It is basically the quantitative measure of wetness of soil mass. There are various methods. The first method is oven drying method. First method is oven drying method. This is very simple and accurate method which is used in the laboratory. So the first point we should remember is it is very accurate. Then it is very simple method which is adopted. Well, in this method what we do is basically we take our soil, we keep it in the oven for 24 hours at a temperature of 105 to 110 degrees Celsius. Then we take it out and measure the weights. Okay, this is the simple procedure. Now let the weight of the container that we have taken is W1. W1 is weight of container. Next, in the container we keep our wet soil mass. Let its weight be W2. So W2 is basically the weight of container plus wet soil that we have just placed in it. Now we keep it in oven and then let it dry for 24 hours and then take it out and then again weigh it. Let its weight be W3. So W3 is basically the weight of container plus dry soil. Plus dry soil. So what is basically the water content? It is weight of water to the weight of soil. So what is the weight of water? If I want to find the weight of water, it is W2 minus W3. If I subtract W2 and W3, I get weight of water. So water content is weight of water to weight of soil. Weight of soil solids. So weight of water is W2 minus W3 and weight of solids is W3 minus W1. So since we express this in percentage, so I am multiplying it by 100. Well, one thing we have to keep in mind is that the temperature should not be more than 110 degrees Celsius, because the temperature higher than 110 degrees Celsius may break the crystalline structure of the clay. Okay. Well, one more thing is there which we should keep in mind, that if we have organic soil such as peat, then the temperature, well, generally we use temperature 105 to 110 degrees Celsius. Okay, but in the case of organic soils, if we have organic soils such as peat, then this temperature should be restricted to 60 degrees Celsius, because if the temperature is more than 60 degrees Celsius, it may cause the oxidation of organic matter present in the organic soil. That is the reason that temperature should be restricted to 60 degrees Celsius. Okay, this is most accurate and most adopted method that we use. Well, next method is sand bath method. Next method is sand bath. Well, this is quick and field method. The one we discussed just before is laboratory method, and this is a field method. Okay, in this the wet soil sample, they are placed in container and dried up by placing it on a sand bath, and we use basically kerosene to heat it up. So basically this method is same as that of oven drying method, except that we are using kerosene. Okay, and of course the water content is determined by the same equation as given in the oven drying method. But one thing we should keep in mind, that heat that we are giving to our soil sample, it should be uniform. Okay, well, now the next method is calcium carbide method. Of course the name says calcium carbide method, so we generally use calcium carbide in this particular method, calcium carbide method, and this method is also known as rapid moisture meter method. Rapid moisture meter method. Okay, in this method we generally take 6 grams of our wet soil sample and we keep it in the moisture tester, that is an airtight chamber. We keep it in that airtight chamber, and then we mix that wet sample with sufficient quantity of calcium carbide powder. So whenever calcium carbide powder is mixed with soil, that calcium carbide reacts with water present in it. So the calcium carbide reacts with water and it forms acetylene gas. It produces acetylene gas. This acetylene gas produced by the reaction of the moisture and the calcium carbide, it exerts pressure on the diaphragm placed at the end of container. Okay, so from that diaphragm we actually get directly the water content reading with the help of this the pressure exerted by the acetylene gas. Okay, well, this method is very quick. It hardly takes 5 to 10 minutes. So basically this is the quickest method. Okay, next is pycnometer method. Pycnometer method. Well, this is generally a method which is used for the soils whose specific gravity is actually known, and this is generally used for coarse grained soils. Pycnometer is basically a density bottle of about 900 ml capacity. Basically it is a density bottle whose capacity is 900 ml. So what we do in this procedure is we take a pycnometer and find its weight. Let us take a pycnometer, empty pycnometer, and its weight be W1. Okay, now we put some 200 to 400 gram of soil sample in it. Okay, we put, this is a pycnometer, and we put some soil in pycnometer plus wet soil. Okay, so we put soil sample. Let its weight be W2. Now we fill the pycnometer to half of its height with water and mix it thoroughly with a glass rod. Then we fill the pycnometer till its top. So basically in third case, we have a pycnometer with our soil sample and pycnometer filled completely with water. Let its weight be W3. This is pycnometer plus wet soil plus water. Then we'll empty this pycnometer and clean it thoroughly and fill it with water completely. Fill this pycnometer completely with water. Let its weight be W4. Now we need to find the water content. We have already discussed that water content is weight of water to weight of soil solids. Okay, now we need to find the weight of water. If I subtract these two terms, like weight of water is, I can write this weight of water as W2 minus W1 minus Ws. So the soil sample weight we have taken, if I subtract the dry soil from it, I'll get the weight of water. Now let me take this equation as equation 1 and this as equation 2. Now the weight of this solids. Weight of solids can be found by removing the soil solids from W3. From here, if I remove the soil solids and replace it by equivalent amount of water, then what I will get? The weight of solids. So if I consider this fourth pycnometer, I can write as W4 is equals to W3 minus Ws plus Ws by G. What I have done is that in the third case, I have removed the soil and filled it with equivalent amount of water. So we can write W4 as W3 minus Ws minus Ws by G. So if I solve this equation, what I'll get is Ws, that too in the terms of W3 and W4. If you solve this value, you will get W3 minus W4 into G upon G minus 1. Let me mark this value as third. If we put second and third in the equation 1, then we will get the value of water content. So I can finally write that water content is equals to W2 minus W1 upon W3 minus W4 into G minus 1 by G minus 1 into 100. So this is basically the water content value found from the pycnometer test. Okay. Now let's go to the next method, radiation method. Next method is radiation method. Well, this is a field method. This method we use in field conditions. Okay. Well, in this method, we generally take two steel casings. Well, if this is my ground on which I have to find the water content of the soil, okay, this is the place where I have to find the water content. So what I'll do is we take two steel casings. First of all, we take two steel casings. Let this be the casing 1. Let me name it as casing A, steel casing A, and one more casing I'll take and I'll name it as casing B. So we basically have two casings, and then what we do is we'll take a device which contains some radioactive isotope materials. Generally we take cobalt 60. It is placed in the casing A. So we lower down a cobalt 60 isotropic material, okay, and in the second one we lower down the detector, which basically detects the neutrons coming from the cobalt 60. So this is cobalt 60. Okay, so when this cobalt 60 is activated, it emits neutrons. And since this is our field, it contains some moisture and it contains H plus ions. So what happens is these neutrons strikes with these H plus ions and they lose some of their energies, and after that they are detected by the detector. So in this method, loss of energy is used for determining the water content. Okay, in this, then from the loss of energy we basically calibrate the value of water content. Okay, well, here we finish our first topic, water content. Next important index property is specific gravity. Specific gravity. We talked about the specific gravity in our last lecture. Okay, the procedure of finding the specific gravity is same as that of pycnometer water content determination. Okay, that means water content from pycnometer. It is same, except that in this case we take the dry soil. So let us take the weight of pycnometer as W1. It is pycnometer weight as W1. Then we fill the dry soil in it. We fill the dry soil in it and let its weight be equal to W2. So W2 is pycnometer plus dry soil. Now again we fill the whole pycnometer with water. This is our soil and I have filled the pycnometer with water. Let me take this weight as W3. So this is pycnometer plus dry soil plus water. So now I'll empty this pycnometer and I'll fill the whole pycnometer with water. Now let us take this weight as W4. So this is pycnometer plus water. Now what is the specific gravity? We have discussed that specific gravity is gamma S by gamma W, that is weight of soil to the weight of equivalent amount of water. So I can take weight of soil as weight of soil. I can find from W2 and W1. If I subtract W2 minus W1, I'll get the weight of soil. So this is the weight of soil. Now I have to find the equivalent amount of water, the weight of equivalent amount of water. That means this volume of water I have to find. Okay, well, to find this volume, what we do, we take W4 and W3 and if I subtract the water weight from W4 and water weight from W3, I'll get the value of weight of water. So if you take the case 4, that is diagram 4, I can say that weight of water in fourth diagram is W4 minus W1, and weight of water in third case we can easily take it as W3 minus W2. W3 minus W2, we can take the weight of water. So therefore weight of equivalent amount of water, weight of equivalent amount of water is equals to W4 minus W1 minus W3 minus W2. So I can rewrite it as W2 minus W1. So I can rewrite it as W2 minus W1 minus W3 minus W4. So therefore we get our specific gravity value as W2 minus W1 divided by W2 minus W1 minus W3 minus W4. Well, going to the next index property, we'll discuss the next index property as in situ density. In situ density. Well, we all know that density is equals to mass per unit volume, or we can say weight per unit volume. There are different methods, out of which the first method that we are going to discuss is core cutter method. Core cutter method. Well, this method is commonly used method and it cannot be used in case of hard and gravelly soils. Well, in this method we have a core cutter of known volume. The volume of core cutter is generally, not generally, it is 1000 cc. Okay? And it is driven into the soil using a hammer. With a hammer we drive this particular core cutter into the soil, and when it gets filled out, we take it out and then we take the weight of the soil inside this core cutter. Okay, so we know the volume of core cutter. We drive this core cutter into the soil and then we take out and take the weight of soil. So now we know the weight of soil and the volume of core cutter. So from these two terms we can easily find the density. So density is equals to weight by volume. From the competitive exams point of view, the thing that you should remember is that it cannot be used in case of hard and gravelly soil. Okay, well, going to the next method is sand replacement method. The name says sand replacement, that means we are going to replace sand by our original soil sample. Well, this method is particularly used in hard and gravelly soils. Hard and gravelly soil. Well, in this method we make a hole into the ground and excavate the soil from it, and then we take the weight of that excavated soil. Let its weight be W. Then to find the volume of that hole, what we do is we replace the soil with the sand. The sand we use is generally Aino sand. So from that we get the volume of that particular hole and the weight we have already calculated. So we know both the terms. So we can easily get our density as weight by volume. Well, third method used is water displacement method. Water displacement method. Well, this method is used for cohesive soils only. This method is used for cohesive soils only. Okay. Well, in this what we do is we take a sample of a regular shape and then we take its weight. Let its weight be W1, and then we coat it with a thin layer of paraffin wax and then we again weigh it. Okay. Let its weight be W2. Well, W1 was the weight of soil sample and W2 was weight of soil sample plus paraffin wax. Okay, because we have coated our soil sample with the paraffin wax and again weighed it. Okay, now the coated sample is placed into a metal container which is filled with water up to the brim. Then when we place this soil sample in it, some of the water is displaced from that container. So that displaced water is measured by measuring jar. So that volume of displaced water will be equal to the volume of sample. So now we know the volume of sample also. So the volume of displaced water be equals to VW, volume of displaced water. So now From this we can find the actual volume of our soil by the formula given below. Okay, this gamma PA is unit weight of paraffin wax. Unit weight of paraffin wax. Now we know the weight, we know the volume, so we can easily find our bulk density, W1 by V. So these are the three methods which are generally used for calculation of, for determination of in situ density. Well, there are three more index properties that we need to discuss, and we'll deal with those three index properties in our next lecture. Thank you. If you have any doubts, you can ask in the comments section given below. Thank you.